Hi, I'm Mark Weitzman, and welcome back to some more problems in theoretical physics and classical mechanics, special relativity. This problem is problem 13 in chapter 6 of the first edition of Goldstein Classical Mechanics, and problem 26 in chapter 7 of the third edition. And the problem reads: show that the relativistic motion of a particle in an attractive inverse square law of force is a precessing ellipse. Compute the precession of the perihelion of Mercury resulting from this effect. The answer, about 7 seconds of arc per century, is much smaller than the actual precession of 40 seconds of arc per century, which can be accounted for correctly only by general relativity. This statement's a little misleading. The actual precession of Mercury is something like 5,000 seconds of arc per century. But most of that can be calculated as due to perturbations from the other planets. When you take away the perturbations from the other planets, as was well known at the beginning of the century, the 20th century, it was well known to Einstein and others that there was 40 seconds of arc per century that was unaccounted for by Newtonian mechanics. And there were various theories, like there was thought that maybe there was a planet Vulcan that was inside Mercury that was causing the perturbation. Some people afterwards and later talked about solar oblateness as causing it. But it turned out, at least in when Einstein calculated the effect, when he had his general theory of relativity in about 1915, 1916, he calculated it and he got the right answer, 40 seconds of arc per century. So that's the general relativity calculation, and it's been confirmed experimentally. What's interesting is that, as some of you might know, in any inverse square law force, the motion of a planet is an ellipse. There's an additional symmetry there, which I may do some videos on one day, about the Lagrangian vector, which keeps the orbit constant in space. It doesn't precess, except for the fact that there are perturbations from other planets. But anything other than an inverse square law force will result in a precessing ellipse. And it turns out you can do the calculation in special relativity. This is not a complete theory of gravity. It's probably not even a consistent theory of gravity. But you can try and do the calculation in special relativity, and that's what this problem does. And you'll end up getting a precession that's about 1/6 of the general relativistic effect. So let me start with the calculations. And we're just going to define our theory. We're going to define it with a Lagrangian equal to minus mc squared square root 1 minus v squared over c squared plus gm m. Big M is the mass of the sun, m is the mass of the planet, over r. For those of you who are familiar with Newtonian, usually we have T minus V. So in this case, V is the well-known Newtonian potential minus G M over R, which leads to the inverse square law of force. As I said, this is probably not a consistent Newtonian potential for special relativity, but for a static it's okay. And then if you expand out this, you'll end up getting minus mc squared plus plus 1/2 mv squared. And so this really is the kinetic energy, the Newtonian kinetic energy. It's 1/2 m plus ... higher order terms. It's the kinetic energy, and we take off the rest mass energy, you know, because in relativity we have a rest mass energy. So when we subtract the rest mass energy, we're just left with the kinetic energy. It's a constant anyway, so it doesn't really matter. So what's interesting is, so in a sense, this is sort of saying that the energy if we didn't have a potential, the energy minus mc squared is equal to T, is equal to 1/2 mv squared. So we can see that this is an okay Lagrangian, at least it reduces to the classical one. And if you actually work with this over here and compute the force laws that you get for a free particle, you'll see that it works out to be the correct one. And this is just the minus of the negative potential. Okay, and we're working in polar coordinates. We're working in the plane of the orbit. We know that it's going to be in a plane. It's very simple. And we're going to have v squared is equal to r dot squared plus r squared theta dot squared in polar coordinates. So let's start calculating. First, we'll define p theta. That's the conjugate momentum with respect to the variable theta. It's the partial of L with respect to theta dot. This is equal to m, and you just take derivatives here, because this v squared, that brings in the theta dot term. So this becomes m r squared theta dot divided by the square root 1 minus v squared over c squared, which we'll just write as gamma m r squared theta dot. So as usual, gamma is 1 over the square root 1 minus v squared over c squared. These are definitions and everything. So this is the usual angular momentum, except it's got a gamma factor. And then we'll define the conjugate momentum for the r variable. It's partial of L with respect to r dot. And again, this comes in because there's an r dot squared and v squared. And this is equal to m r dot over the square root 1 minus v squared over c squared, which is equal to gamma m r dot. Okay. So the fact that the the usual Lagrange equations of motion, d dt, partial of L with respect to q dot, minus the partial of L with respect to q equals 0. So if q doesn't occur in the Lagrangian, then we have a conserved canonical momentum. So in this case, theta is the only variable that doesn't occur in the Lagrangian. So we're going to have p theta squared. So let me write p theta is equal to gamma m r squared theta dot is equal to a constant. Okay. Now the next equation of motion that we have for the r variable, d dt, gamma m r dot, that comes from taking r as the momentum variable, the canonical momentum variable, minus m r theta dot squared, should put a gamma here, plus, so here we're just taking the derivative with respect to r, and again, because r is part of v, because it's r squared theta dot squared, we are going to get a derivative of this term with respect to r, which gives me that. Then I have plus the potential term, GMM over r squared equals 0. So obviously we can now express theta dot in here, and so we're just going to get an equation for r. So we're trying to solve for r as a function of theta, and then we're going to make a definition very soon, u equal 1 over r, just as you do in the usual Newtonian problem. We're going to make that definition, so we're going to look for functions u of theta when I get the final differential equation. So what we do is we just use basic chain rule in calculus, d dt equal d theta, d theta dt is equal to theta dot d theta, which is equal to, now we substitute from here, equal to p theta over gamma m r squared d theta. Okay, now using u equal 1 over r, we find du d theta is equal to minus 1 over r squared dr d theta. So dr d theta is equal to minus du d theta over u squared. We'll have use for that in a second. So using these two things, the ddt and this dr d theta, if we substitute in here, we get a differential equation. So we're going to start with p theta over gamma m, and then for the r squared we just make that u squared. And then we have the ddt term, which we'll use over here, dd theta we have the gamma m, and now we have the r dot. Well, first of all, we have gamma m p theta over gamma m r squared. And this is, and then we have the we're going to have dr d theta, which is minus du d theta over u squared. And then the next term in our differential equation, minus gamma m p theta squared u cubed over gamma m squared, I'm sorry, plus, I'm going to write 0 equals plus g m m u squared. So as you can see, a lot of things simplify here. Like the r squared, u squared is 1. The gamma m's cancel. And I can take the p theta out since that's a constant. And then I'm going to have u squared. I can divide by u squared. That will leave a u term here. This term will come out. So when all is said and done, we get a fairly simple differential equation. Simpler than the one we would get in general relativity, where you would have to use perturbation techniques. Well, you could solve it exactly, but it's easy to get the answer by perturbation. But this is the orbit equation. d2u d theta 2 plus u equals g m m over p theta squared times gamma m. Now, at first, the way it's written, you say, okay, this is great. Nice linear equation, constant on the right side. No, it's not a constant on the right side. Gamma equal to 1 over the square root 1 minus v squared over c squared. And remember, v squared is equal to, dr dt squared plus r squared d theta squared. Squared d theta dt squared. So we're definitely, it's nice to write it like gamma, but it's definitely not a constant, but we're saved. Because we can write, and you can easily verify this, we have another first integral, which is conservation of energy. The energy conservation, the relativistic energy, total energy for the moving particle is just gamma mc squared minus the potential energy. So this is conserved. This will give us gamma m, which we can substitute in there. So we get from this equation gamma m is equal to 1 over c squared E plus gm m over r. So now we can substitute this in there. And when we do that, we get the real orbit equation. d2u d theta 2 now save one step here, plus u times 1 minus g m m over c p theta squared, and this is equal to g m m e over p theta squared c squared. This is a nice equation. Okay, so this is our orbit equation. Now, when you're a theoretical physicist, first thing you should do is you should make sure this equation makes sense. So I want to see if it reduces to the Newtonian orbit equation when velocities are slow or the speed of light is infinity. So the Newtonian orbit equation, you can look it up, is d2u d theta 2 plus u equal g m m m over L squared. And I want to compare that to that. Well, first of all, when the motion is slow, E over c squared is basically the rest mass. So we will get that other extra m there. P theta squared is equal to gamma m r squared theta dot, not p theta squared, just p theta. And that basically goes to the angular momentum L when, gamma goes to 1. Basically, that's the angular momentum, because the mass, you could consider like the relativistic mass as being gamma m. So on the right-hand side, we get the same thing we have here. That's good. On the left-hand side, we have u. Here we have this other thing. I'll leave it to you to show that this 1 over c squared basically kills this other thing and it goes to 1. So this is good. Our equation basically reduces to the Newtonian mechanical equation. And now we just want to solve the equation. So I want to rewrite that equation. First of all, I want to define capital gamma squared equal 1 minus G M over C P theta squared. I want to define another constant D as equal to G M E over C squared P theta squared gamma squared. So on the right hand side what we have is basically D gamma squared. So our equation, the equation we're trying to solve is just D2U D theta 2 plus U times 1 minus, U gamma squared is equal to D, GMM, okay, is equal to D gamma squared. Not sure I did that right. Okay, so the solution to this is very easy. I should have D on the right hand side. I don't know why. Did I leave something out? Well, it doesn't really matter. Okay, I figured out my mistake. Sorry about that. This should be D gamma squared, because D gamma squared is GMME over P theta squared C squared. So the homogeneous part without the D gamma squared, it's just the usual cosine equation. It's given by this part. I left out the phase angle because that's not important. And pretend the phase angle is 0. And then the particular solution is U equal D, because then this is canceled and I get D gamma squared equal D gamma squared. So the total solution is U, which remember we're defining as 1 over R, is equal to D plus A cosine gamma theta. And we can write that down as D times 1 plus A over D cosine gamma theta. Okay. So, there should be 2 parentheses here. So this looks familiar. And if this gamma were 1, you'd say this is the equation of ellipse. But gamma is almost 1, so this is what will give us the precession. We're going to treat this as an ellipse now. What we have to do is we have to identify the parameters. So if this was 1, then A over D would be equal to the eccentricity of the ellipse, and also we could write the semi-major axis A. I want to put it in terms of no parameters. It's equal to 1/2. Remember the definition of this R max plus R min, and that's going to be equal to 1/2 1 over d plus a plus 1 over d minus a. And this ends up being equal to d divided by d squared minus a squared. So using the eccentricity in that formula, we end up getting that d is equal to 1 over a 1 minus epsilon squared. Epsilon is the eccentricity. And our orbit equation becomes u equals 1 over r is equal to 1 plus epsilon cosine gamma theta divided by a 1 minus epsilon squared. So now we have everything in terms of the parameters. A is the semi-major axis, epsilon is the eccentricity, gamma is some parameter which is close to 1, which will give us how much the thing precesses. So let's calculate that right now. So when theta equals 0, we have cosine gamma theta equals 1. So that's sort of like the maximum for our, let's say this is, I'm not good at drawing ellipses, that's for sure. Let's say this is the focus. So that's where we are when theta equals 0. And then we want to know when it's again at, when this is again at maximum. So we want at theta equals theta prime, we want cosine gamma theta prime to be equal to 1. That will happen when gamma theta prime is equal to 2 pi. So theta prime, the next angle, is equal to 2 pi over gamma. And notice that gamma, I don't have the definition on the board anymore, but it was 1 minus something small. So gamma is less than 1. That implies theta prime is greater than 2 pi. So on the next orbit, the maximum is going to be somewhere like, over here at an angle theta prime, and that gives us our precession. We expected it to be at 2 pi if it was like Newtonian. So the precession angle, del theta, is equal to 2 pi over gamma minus 2 pi. That's how much we precess each orbit of the planet. And I'll write down that definition for gamma squared. Gamma squared equal 1 minus GM M over C. I'm going to stop writing, okay, I'll do it now, but over CP theta squared. Okay. This implies, since this is small, it's binomial expansion for the square root, this implies gamma is 1 minus 1/2 GM CP theta. So now we have our precession in terms of gamma, and we're on our way. So let's do the computation. I found this part of the problem, keeping all the constants straight and relating them to real world values, harder than actually solving the problem. So we have del theta, and this is per orbit, It's 2 pi. Let's substitute in the value of gamma. 1 minus 1/2 GMM over C. I'm now going to use L for P theta squared. It's not exactly right, but this is a small quantity and it makes an even smaller error, so this is okay. Minus 2 pi, which is approximately equal to, we can 1 over 1 minus x is 1 plus x, so we're going to get 2 pi times 1, we subtract off that, then we have the 1/2, so it's just 2 pi over 2 GMM over CL squared, and this is equal to pi GMM over C squared L squared. Okay. Now we want to use Kepler's laws. So Kepler's first law, if you remember it, it's just equal areas in equal times. So basically it's saying that the derivative of the area with respect to time is a constant, and this constant, you know, if you ever use polar coordinates, let's say this is R and this is small, this is like d theta. Well, the area of the triangle is just 1/2 r squared d theta, and then per unit time, so it becomes, per unit time becomes 1/2 r squared d theta dt, which is equal to L over 2m. Okay, remember our definition of L is mr squared theta dot, so it's L over 2m. So in one period, if we would integrate this over one orbital period, the time is the period tau, we're going to get L over 2m times tau is equal to the area. I should write area here. It has nothing to... I was never dyslexic when I was younger, but as I get older, I'm getting more dyslexic. So it's the derivative of the area. So this is just the area. And the area of an ellipse, you should remember this formula. If not, look it up. It's just pi a squared times the square root 1 minus epsilon squared. Okay. So this gives us our parameter L that we have in here. I want to get rid of. Now I have it in terms of the eccentricity and the mass. So so L is equal to 2m pi a squared square root of 1 minus epsilon squared over tau. Okay. Now, I know we introduced another parameter, tau is the period, but now we use Kepler's third law. And I'm not going to derive this. I mean, this is all in Goldstein chapter 3. But he shows that tau squared, if you remember, the period squared is proportional to the cube of the semi-major axis, and you can work out the proportionality of the constant. So this is Kepler's third law. So now things are starting to look good. So let's go back to our formula here for del theta. Del theta is equal to pi over c squared. I have a GMM here. GMM. And now I have to put L squared in the bottom. So I'm going to have 4m squared pi squared a to the fourth 1 minus epsilon squared, and then tau, which would be over here, goes to the numerator, tau squared, and tau squared gives me 4 pi squared a cubed Every time I do this, I get something different than my notes. Okay, this is obviously wrong. This is pi GMM squared, c squared, L squared. I should have pi over there. Then I get tau squared, 4 pi a cubed over GM. Okay, so there's lots of cancellations here. 4 pi squared cancels out the 4 pi squared there. The GM cancels out this 2 here. And a cubed cancels out the 4 there. So we're left with pi over c squared. And now we have an m here, cancels out that 2 there. Pi, I did something wrong there. Okay, yeah, only supposed to cancel out the GM part, not the m squared. So m squared cancels out the m squared there. So I got pi GM c squared a 1 minus epsilon squared. That's our answer. Now, if you look in a general relativity book, you're going to get 6 times this. So for GR, it's just times 6. And that gives you about 40 arc seconds per century. So this thing ends up, you can put in the numbers if you want. You put in the solar mass, Newton's gravitational constant, semi-major axis for Mercury, and the eccentricity for Mercury, and you will get about 7 seconds of arc per century. So there's nothing really difficult about this calculation except keeping all the constants straight. And it's a nice little problem. It just shows that I don't know if this calculation was done before Einstein. I don't think anybody did this calculation before Einstein did his general relativity one. If they had, they would have said, well, we got close. We got 1/6 of what we need. And that's when theoretical physicists start fudging around and seeing how they can add extra things. But it wasn't necessary. Einstein did the calculation, straightforward, got the right answer right away. Okay, I will see you in some future videos. Thank you for watching.